In the last lecture, we learnt about mass defect, binding energy and binding energy per nucleon. Mass defect, you recall, is the difference in the mass of combined nucleons minus the mass, actual mass, observed mass of a nucleus. Mass defect multiplied by c squared according to the Einstein's formula gives us the binding energy, and divide that by the number of nucleons in the nucleus gives us the binding energy per nucleon. And we plotted binding energy per nucleon against the mass number, and we found why on one side the fission reaction takes place, on the other side fusion reaction takes place. And the more important thing that we discussed was the possibility of nuclear fusion in the laboratory, because that would give us a very abundant and clean source of energy. And the process being studied is deuterium plus tritium, and they would combine and fuse to give us helium and a neutron and lot of energy. But to make them combine, you have to heat them to high temperature and also to confine them in a certain space, so that they can react. So, it is a difficult thing. All many labs in the world are doing this, and maybe someday in the near future we shall have this process. Now, a common term for nuclei and their isotopes is nuclide, NuClide, nuclide. And the stability of a nuclide would depend on the number of protons and neutrons. You see, I told you in the last lecture also that both protons and neutrons are necessary in the nucleus. You cannot have a nucleus consisting only of protons, more than one. Hydrogen of course has one proton, but more than one protons. And you can't have a nucleus consisting only of neutrons. Why? Because the protons repel each other. If there are no neutrons to increase the distance between the protons, then the nucleus would break. Similarly, if there are no protons, only neutrons, then the nuclear force, the strong nuclear force between them would break the nucleus once again. So, both protons and neutrons are essential for the stability of a nuclide. Both neutrons and protons participate in attracting one another through the strong nuclear force. The force attraction binds them in the nuclides. Because of dual role of neutrons, larger number of neutrons than protons are required to stabilize the nuclide. You see, he said because of the dual role. What is the dual role of neutrons? One, they tend to increase the distance, they come in between the protons, they tend to increase the distance between the protons, so that the repulsion is reduced. And second, then they provide the nuclear force, so that all the nucleons can forge bonds between them and become a stable nucleus. So, neutrons have dual role, and therefore, you would need larger number of neutrons than protons to make a nucleus stable, to make a nuclide stable. Around, I will show you this. We have plotted here the neutron number and the proton number, n and z, neutron number and proton number. And you see that this thick line, this thick blue line, that is the stability, line of stability. Nuclei lying on that line are stable nuclei, and around that line there is zone of stability. All nuclei in this zone, this dotted lines, all nuclei existing in this zone of stability are stable nuclei. Outside this, the nuclei are unstable. On this side, there are more protons than neutrons, and on this side there are more neutrons than protons. So, since there are more protons here, the protons must decay to become neutrons. That means, they must emit positrons or beta positive particles. On this side, nuclei must emit electrons or beta negative particles, so that neutrons are converted into protons, and the nuclei migrate towards the zone of stability. So, let us see what are the conclusions from the figure, from this figure. Look at it carefully again. This blue line is the line of stability. All nuclei lying on this line, existing on this line, are stable nuclei. And you can see also that for stability, the number of neutrons is slightly higher than the number of protons, as I have said earlier. And around this line of stability is a zone of stability. All nuclei lying in this zone are stable nuclei. So, what are the main conclusions? The lightest nuclei have protons and neutrons almost equal numbers. In the beginning, this is n equal to z line, and you can see this line coincides with the line of stability for lighter nuclei. So, for lighter nuclei, number of protons is equal to the number of neutrons almost. The heavier nuclei require more neutrons than protons for stability. This line I have already pointed out that on this line the nuclei have more neutrons than protons. So, the heavier nucleides require more neutrons than protons for stability, otherwise nucleus would explode. Nucleides falling outside the zone of stability are unstable. Here and here, here and here, they are unstable. And decay of unstable nuclide produces nuclide nearer to the stability line. I said earlier also, on this side there are larger number of protons than necessary. So, the proton must decay to become neutrons, so that the nucleus migrates towards the line of stability or zone of stability. On this side there are more neutrons than necessary. Neutrons therefore must decay to become protons, so that again the nucleus or the nucleide migrates towards the zone of stability. So, these are the main conclusions of this curve. And as I said, nucleides falling outside the zone of stability are unstable, and those where the number of neutrons is higher, then the neutron breaks into proton plus with the emission of a beta particle and a neutrino. On the other side, if there are more protons, then protons must combine with either electron, or they must capture either an electron or emit a positron to become a neutron. So, here the proton emits a positron and becomes a neutron. Here a proton captures an electron and becomes a proton. So, the idea is that the proton must become a neutron by either emitting a positron or capturing an electron. So, here P plus E is equal to n, here P equal to n plus positron plus neutrino. So, we have these two equations here, and alpha emission nuclei, unstable nuclei can also emit alpha particles, and there this nucleus X becomes Y, whose mass number is smaller by 4 and atomic number is smaller by 2. This we have seen earlier also, and alpha particle of course has mass number 4 and atomic number 2. Then there are certain magic numbers 2, 8, 20, 28, 50, 82, 126. What is the meaning of magic numbers? If the number of nucleons in the nucleus is equal to one of these numbers, or the number of both protons and neutrons are equal to one of these magic numbers, then the nuclear is extra stable. If the number of both neutrons and protons in a nuclide is one of the magic numbers, say 20 neutrons and 20 protons, or 20 neutrons and 8 protons, and like that, then the nuclei is particularly stable. An example is this 208 lead, which contains 82 protons, 82 is one of the magic numbers, and 126 neutrons, which is also one of the magic numbers. So, the number of protons as well as the number of neutrons both are magic numbers, and therefore, this is a very stable nucleus. Other examples are helium 4, oxygen 16. I will give you an example of oxygen 16. Oxygen 16 has several isotopes, and you see the most stable one is there, a number of neutrons. There are 8 neutrons and there are 8 protons. So, this is both 8 number of neutrons as well as number of protons, both are magic numbers, and therefore, this isotope of oxygen, which has atomic number 8 and mass number 16, is the most stable of all other isotopes. That is the magic of magic numbers, one may say that the number of protons in this isotope is 8, number of neutrons in this isotope is also 8, both are magic numbers, and therefore, this isotope oxygen is the most stable compared with the other isotopes of oxygen. So, this is the magic of magic numbers. Now, let us take this topic of radioactivity. See, those nuclei which are unstable, they decay spontaneously. In fact, they decay, and the decay products are more stable than the original nucleus. And what do? They emit mostly alpha, beta and gamma. Actually, as I said in the last lecture, they can emit also other particles like electrons, positrons, protons, neutrons, etc. They can emit other particles also, but these are the most frequent, alpha, beta and gamma. That is why they are famous, well known. So, a radioactive material would spontaneously decay and emit these particles. When this was discovered long back in the 19th century, then one did not know the nature of the alpha particles and beta particles and gamma particles. And what they did was, they let this emission, alpha particles, beta particles and gamma particles, pass through a magnetic field. And there is an interaction between magnetic field and a moving charge. Magnetic field in this case is into the screen, it is into the screen, and the alpha particles are coming like this from V cross B. You can see they would deflect in the upward direction. So, the particles deflecting in the upward direction were found to have, or were concluded to have, positive charge, and those which deflected downwards, they had negative charge. And radiations emitted by a radioactive nucleus, radioactive material, here placed in a lead chamber, they were the radiations by this radioactive material, they were passed through a magnetic field, and from the interaction of the magnetic field with the moving charges, we know that if the charge is positive, then it will be deflected upwards, and if the charge is negative, it will be deflected downwards. So, from this they found that alpha particles have positive charge and beta particles have negative charge, and gamma rays have no charge. Secondly, since this deflection is much smaller than this deflection, they found that alpha particles are much heavier than beta particles. In fact, later on it was established that alpha particles have mass number 4 and the charge 2 units, and these gamma particles are actually electrons, negatively charged electrons, and gamma rays are electromagnetic rays just like light rays, except that the frequency of gamma rays is very high, and therefore, their energy is very high. Now, if we have N0 nuclei of a radioactive nucleus, then the rate at which they decay, dN by dt, that is proportional to the original number N0, and lambda is a constant of proportionality. dN by dt is minus lambda times N0, and lambda is called decay constant. Why it is called decay constant? Because if you integrate this equation, you see n is equal to N0 e to the power minus lambda t, that is, the number N0 is decreasing. That is why this lambda is called a decay constant, and this negative sign here also indicates that this n is going to decrease with t. As time increases, the number of nuclei would decrease, and this is the equation that tells us the rate at which the nuclei would decrease. This is important thing to remember, that radioactive decay is a random process. It is not that the nuclei of a given kind decay together. You see, if we have a nuclei, say, of a given kind which are radioactive, then this nucleus, for example, may decay, but this may not. This may decay a little later or a little earlier. So, the decay process is random, and therefore, the whatever we say about life or half life of these would also be probably so. They will also have the probability attached to them. Suppose the number of nuclei becomes 1/eth in time tau, then what happens? Then n by n0, from this equation n by n0 is 1 by e the number becomes 1/8, which is e to the power minus 1, which is e to the power minus lambda t. That means 1 is equal to lambda t, that is tau. Tau is 1 by lambda. That is, tau is called the mean life of the radioactive nucleus. It is the average expected time before the nucleus decays. Why average expected time? Because the decay, radioactive decay, is a random process. Therefore, all the nuclei do not decay at the same time. Therefore, we can talk only of averages. Suppose the number of nuclei becomes half of the initial number, that is, n by n 0 is half. Then our equation is half equal to e to the power minus lambda tau half, or tau half we can find from this equation is 0.693 times tau, where tau is the mean life. So, half life is the average expected time for half of the radioactive nuclei to decay. This is just the average time, as I said, because the process is random, they do not decay at the same time. From what has been said above, the mean life and half life of a nucleus, it follows that if we keep say 10,000 identical radioactive nuclei, each in a large number of boxes, we have several boxes, each one containing 10,000 identical radioactive nuclei. What will happen if we open them after their half life? Half life, let us say 1 minute or 2 minutes or 10 minutes, we open them after that time and find. Then each box will contain nuclei in number about 5,000, not exactly 5,000. Some may contain slightly less than 5,000, some may contain slightly more than 5,000. The average number of all these large number of boxes would be 5,000. So, that is why I said half life is the average half life of all the nuclei. So, the number in these boxes will not be the same. One, in some it may be slightly higher, in some it may be slightly lower. The average number would be 5,000. So, that is, when we talk of half life, we say half life is the average expected time or probable time for half of the radioactive nuclei to decay. Tau half, once again to emphasize, tau half is called the half life of a radioactive nucleus. In this time, what happens in this time? If there are 10 nuclei, they become 5, that is, the number becomes half. Suppose we start with 32 grams of radioactive sample, any radioactive sample, and suppose its half life is 5 seconds. So, what will happen after 5 seconds? 32 by 2 will be left only with 16 grams, approximately 16 grams. What will happen after another 5 seconds? Half of 16 grams, that is approximately 8 grams would be left, and after a lapse of another 5 seconds, half of 8, that is about 4. So, in 3 half lives, 5 second, 5 second, 5 second, in 15 seconds, the amount of radioactive substance left will be 1 by 2 to the power cube, or 1/8 of the original, that is 32 divided by 8 will become 4. So, at the end of 3 half lives, the material left would be roughly or approximately 4 grams. This table shows that after 1 half life, the number that is left behind is n 0 by 2. After 2 half lives, the number left behind is n 0 by 4. After 3 half lives, the number left is n 0 by 8, and so on. So, after n half lives, the number left behind is 1 by 2 to the power n into n 0, and this shows graphically how a material decays. This is in arbitrary units, and you can see that if n by n 0 is 0.5, then half life is this in these units, and if they are left behind say 1/8, then this is the mean life tau. So, you can see this is the way they decay. This is an exponential decay, and I have collected here for you half lives of a few important nuclei. Carbon 14 has a half life of 5730 years, 5730 years, and this is a very important isotope. This is used for dating of fossils. Fossils are long dead organisms, and they are buried inside the earth, and they become fossils. And if we discover one, we have to find how old this fossil is, and there we use the dating, carbon 14 dating. Phosphorus 32 is used in detection of tumors in the human body. Cobalt 60 is used in treatment of cancer. Iodine 131, half life of 8 days, is used in treatment of hyperthyroidism. If somebody suffers from high thyroid levels, then this is used. And uranium 238 with a half life of 4.5 billion years, 4.5 into 10 to the power 9 years, they are used for geological dating, that is geological era, which are given in millions of years. Carbon, as I said, is carbon 14 is very interesting. So, I have chosen to explain to you the carbon dating process. Carbon has 15 isotopes, only 2 of which are stable, and these are carbon 12 and carbon 13. Carbon 12 is almost 100%, that is 98.93%, and carbon 13 is just 1.07%. And this is carbon 12, which is the source of our atomic mass unit. I told you at that time that this is the most abundant of carbon isotopes. The remaining isotopes are radioactive, C14 being the most long lived radioisotope. Its abundance is 10 to the power minus 12 of the abundance of carbon 12. 10 to the minus 12 is a huge, very small number. Its half life is approximately 5,730 years, and it is also the most well known of radioisotopes for its use in dating old fossils and archaeological tools. I mean, for example, tools of stone men and so on, because they made tools of stone or wood or something, and they are now buried, they become fossils. So, we can date them, we can find how old they are. Now, how do you produce nitrogen 14? Nitrogen 14 comes from this process. You see, you must have heard about cosmic rays. Cosmic rays come from outer space. We do not know yet the exact origin of cosmic rays, but the cosmic ray particles have huge energy, and when one of those particles reacts with the particles of the atmosphere of the earth, they produce a huge number of secondary particles, and this is called a shower actually, because the number of these secondary particles is so large that it becomes a shower. So, these are called showers, and one of the particles which cosmic ray particles produce in interaction with the atmosphere particles is neutron. This neutron is captured by nitrogen 14 with the emission of a proton, and therefore, this becomes carbon 14. So, the production of carbon 14 is through this process. The neutron that is produced combines with nitrogen 14, emits a proton, and the product is carbon 14. That is how carbon 14 is produced in nature. And the natural process of production of carbon 14 ensures that the ratio of carbon 14 to carbon 12 remains steady at around 10 to the minus 12. I told you the abundance of carbon 14 is about 10 to the minus 12 compared with the abundance of carbon 12. So, this natural process of production through the interaction of atmospheric particles with cosmic rays keeps this ratio constant. In the next lecture, we shall continue with this. We shall find out how carbon 14 enters our bodies and other organisms, and how we can use the existence of carbon 14 in other fossils to find out how old they are. In this lecture, of course, we have concentrated on the stability of the nucleus again, and we have found the a radioactive nucleus decays like this. We have defined the half life and we have defined the mean life. Remember, half life and mean life are both average times, average time in which the number becomes half, or average time in which the number becomes 1/100th, because the process, radioactive decay process, is random. It is not that all the nuclei would decay at the same time, they decay randomly. That is why the half life and mean life are given in terms of mean number of years.